Okay, the first question we are going to ask ourselves is, what is water flooding? That's the first question we need to answer. Water flooding is a secondary recovery mechanism. So what we have to realize is, generally, when a well is put on production, it flows naturally. That means there's some kind of mechanism within the reservoir that causes the fluid to flow naturally from the reservoir into the wellbore. Okay, so if a well is put on production, it flows naturally. That's a tendency. But when the energy of the reservoir dies down, there are some mechanisms that can be put in place to re-energize the system. Like if you look at what we have here, we have the primary recovery. That means it is using the primary energy of the reservoir. That's what we have to realize there. So in this particular case, it is flowing naturally. If there is an issue with the wellbore, we are going to set in an artificial lift. I'm going to explain those two terms shortly. Now, when the natural energy of the reservoir dies down, they have to look at
Yes, sir.
okay. All right. So let's come back to what I was talking about. So now when the natural energy dies down, they have to look at other means of re-energizing the reservoir. And from the primary recovery methods, now they have to move now to the secondary recovery methods. And these secondary recovery methods now involves what we are going to discuss today, which is water flooding. So we have basically two types. We have water flooding and water injection. The water injection is based mostly on for reservoir. So we have water injection and we have water flooding. I will explain those two terms in a brief. So generally, we have less than 30% of recovery when these two methods are applied. We have less than 30% of recovery. When the secondary mechanism comes in, we have between 30 to 50% of recovery. Now, when they now apply the water flooding methods, it also gets to a point where water flooding now cannot solve the problem, especially in a situation where we may have heavy oil, because this water flooding is what we call cold oil recovery. It's cold because there is no extra heat that is applied. And this method is applied generally in a situation where we have light oil. The oil is not heavy. But if the oil is heavy, we have other mechanisms that we may apply. We have the thermal mechanism, we have the gas injection, and all of that. So when the secondary mechanism fails, they now have to go now into the tertiary recovery. So you realize that from beyond the secondary recovery is what we call the enhanced oil recovery. That's what we call enhanced oil recovery. Beyond the primary recovery, everything that starts from the secondary is what we call the improved oil recovery. So these are other techniques that are applied beyond the primary methods. Now, let's look at what are the sources of this energy that causes the reservoir to flow naturally. Because we have talked about primary energy. What are the various sources of this primary energy we need a reservoir? The first is we have rock and fluid expansion. Remember that during drawdown, as hydrocarbon is gradually leaving the reservoir into the well ball, there is a pressure drop within the reservoir. Generally, if you hold something and you squeeze it, you are applying pressure. If you release the pressure or you open your hand, the pressure that is applied on that particular thing is relieved. What happens is that thing expands. So generally, when pressure is released on a material, the material expands. So if the pressure within the reservoir drops, the rock expands and the fluid expands. So as the rock now expands, what it does is that it squeezes the pore spaces. It closes the pore spaces. So in the course of closing up the pore spaces, it forces the fluid that is found within the pore spaces to escape or to gradually migrate out of the pore space. As a result of that, it gradually moves now into the well bore. So here we are talking about rock and fluid expansion due to pressure drop. So as the pressure is dropping, the rock is expanding, the fluid also is expanding. The next now is solution gas drive. Remember that we have a particular pressure which we call our bubble point pressure. Above the bubble point, there is no gas that exists within the reservoir. Everything has gone into solution. There is no gas. When the reservoir pressure drops, when it gets to the bubble point and below the bubble point, slightly below the bubble point, gas bubbles now starts evolving from the oil. We have gas now that starts coming out from the oil because the pressure is going now below the bubble point pressure. As these gas bubbles start coming out, what they'll easily do is as they come out, they expand. As pressure is dropping, the gas bubbles are expanding. They are expanding. So in the course of that expansion, they are gradually pushing hydrocarbon away towards the well bore. As time goes on and more gas bubbles are being formed, they will gradually migrate upward because gas has a very low density. So what the gas will do is it will easily migrate upward and accumulate at the top of the oil to form what we call a gas cap. So when that gas cap is formed, as pressure is dropping, the gas cap is also gradually expanding. As it is expanding, it is now pushing oil away from the reservoir into the well bore. So that gives us what we call the gas cap drive. We also have what we call the water drive. We know that generally within the reservoir, there is segregation of fluids. We have the lighter gas that flows, that accumulates up. We have the oil in the middle, and we have water down. So as time goes on, the water gradually pushes upward. We have two types of water drive. We have the H water, where we have it in this particular form. We have the edges in this particular form. Then we have the bottom water when the aquifer is around this particular level. But when it's around this level, we call it the H water drive. But at this particular level, we call it the bottom water drive. So it is the gradual movement of the water into the oil reservoir. That gradual movement of water also pushes hydrocarbon away from the reservoir into the borehole. Then the last type now is gravity drive. So it's a movement due to gravity. So I've already talked about gas cap and this segregation of fluids that causes fluids of lighter weight to actually move upward and accumulate at the top of it. So if we have an inclined reservoir, you realize that at the top of that inclined reservoir, we have gas that has gradually... Someone's mic is disturbing, please. Gamti, your mic. Okay, so when we talk about gravity, if the reservoir is inclined, you realize that due to that inclined nature, lighter gas will easily flow and accumulate up that part. And then we have oil in the middle, then we have water at the bottom. So we may have something like an inclined reservoir like that. We have gas up there, then we have oil there, then we have water. So it's going to be our gas oil contact, then it's going to be our oil water contact. Okay, so these are the primary source of energy within the reservoir. If a reservoir is flowing naturally, then it has to be a combination of one or two or three or even all of these particular sources that combines together to produce that particular, to ensure that that particular reservoir is producing naturally. But remember, as time goes on, the reservoir gradually loses its source of primary energy. It gradually loses out. When it gets to a point where these energy sources cannot provide enough energy for the hydrocarbon to move to the well ball, we may now bring in our secondary method. Now, if we go back to what we did last week about system performance nodal analysis, you realize that if a particular system is functioning naturally, then there must be an intersection between the inflow performance relation and the vertical lift performance. If there is no intersection between these two curves, then there is no way that reservoir will perform naturally. So this is exactly what we have. In this particular case, we are talking of a dead well. There is no way it can perform naturally. So there are two things that you can do in this system. Either you cause this vertical lift curve to come down so that there's an intersection, or you cause this IPR to move upward so that there's an intersection. So it is all based on your analysis to see what is supposed to be done in order to re-energize that particular system. So if we are talking of the primary energy of the reservoir being the natural cause of the fact that the well is dead, then our main interest now will be on the inflow performance relation, how to rearrange this inflow performance relation so that the well can flow naturally. That's what we are talking about. So first thing is, what is causing the reservoir or the particular well to be dead? Is it the reservoir or the well ball? If it is the reservoir that is causing it to be dead, it means that all of this energy must have died down. So we need now to shift this particular IPR upward so that it will intersect with the vertical lift performance. In that particular case now, the well now can flow naturally. That's when water flooding now comes in to now provide an extra energy to the reservoir so that this particular curve now will shift upward. If it shifts upward, it will now intersect with the vertical lift performance. But if this IPR is fixed and is okay, and every analysis shows that the reservoir is functioning better, then our problem now is with the vertical lift performance. That means we have a problem inside the well ball, not the reservoir. If there's a problem inside the well ball, then we don't have any business with the IPR. Our essence here is to characterize this particular curve in such a way that it can shift downward to intersect with the IPR. In that case, we now bring in what we call an artificial lift. An artificial lift are not artificial sources of energy that are placed inside the well ball to re-energize the fluid that is inside the well ball so that it can give it an extra push so that it can easily flow from the bottom of that particular well ball to the surface. So there are various types of artificial lifts. Remember, our essence here is not to talk about natural energy or artificial lift. Our essence here is to talk about water flooding. But you need to understand why water flooding has to come in. That's the reason why I had to just take time to explain all of these concepts. So there are basically three types of artificial lift method. We have the sucker rod pump. This is the first one. we have series of systems at the surface that transfers energy. We have something like a belt here, like this, and our normal grinding machine that turns, the belt turns, and then when it turns, this particular system, this sucker rod pump is forced now to perform up-down motion. When it performs up-down motion, we have series of interaction that occurs around here that gives the hydrocarbon inside the well bore an extra push so that it can move to the surface. I don't want us to go into all of this. Then we have electrical submersible pump. We have electrical submersible pump. We have a pump at a particular depth. This pump is rotating. When the pump is rotating, that means it converts the linear motion of the oil into rotational kinetic energy. So it converts linear kinetic energy into rotational kinetic energy. We have series of these rotational pipes that are connected at different levels. So it pushes the fluid from one blade. Let me use that word blade. It pushes the fluid from one blade to another blade. We may have about 5 or 4 blades that are placed. So it pushes the fluid from one blade to another blade. The blade keeps turning. It takes it to another blade. When it now gets now to the last blade, the rotational kinetic energy is converted back into linear kinetic energy that pushes now the fluid to the surface. Then we have the last type, which is most common. I'm not going to talk about those that are not common. We have the sucker rod pump, electrical submersible pump, and the gas lift. Those are the most common. Remember that when you introduce gas into our piping system, the gas goes in to reduce the density of the fluid that is found inside the tubing. And if the density of the fluid that is found inside the tubing is reduced, then the hydrostatic pressure of the fluid inside the tubing also reduces. If you go back to our session of last week, you understand this better. Even the 2-day nodal analysis course that I gave, if you follow it, you understand it better. So we have a system where the gas is injected inside the annulus. The gas is injected inside the annulus. Then we have an operating valve, probably at this level. There are a series of steps that are taken to determine the depth of the operating valve. We cannot go into that. We are going to organize an extra training on the artificial lift method. So the gas is pumped inside the annulus. The gas comes in to the operating valves, then gets into the tubing. Then it now goes and mixes up with the liquid inside the tubing and reduces the density so that it can easily flow upward by buoyancy. So it can easily flow upward by buoyancy. So away from the natural source and the artificial lift method, our essence of this class is our water flooding. So our water flooding, I've talked of, when we talk of water flooding, there are two. People may always confuse between water flooding and water injection. Some may say they mean the same thing, others will say they mean two different things and all of that. But generally, what I know is that there is a difference between water injection and water flooding. Water flooding, we have an injection well and we have a producing well. You now inject water in the injection well, the water gets into the reservoir. As the water is pushing inside at high pressure, it is gradually pushing the fluid away from this particular zone into the producing well. But when it comes to water injection, you are injecting water into the aquifer to maintain the pressure, because this aquifer also has a pressure that it provides. We have already talked about the water drive mechanism. So when it comes to water injection, you are injecting water into the aquifer for pressure maintenance, to maintain the pressure of the aquifer. So that's water injection. But for water flooding, you are injecting it directly into the reservoir where the oil is. You are injecting it directly into the oil zone so that it gets in and pushes the oil from that particular zone towards the producing well. So now, generally, I explained about the profile The profile, when I was talking about the decline curve analysis on Saturday, I explained how generally the production profile looks like. This is our decline phase of the production profile. So when they realize now that the natural energy, the primary energy of the reservoir is already dying down, that means the production rate is reducing. Then what they will do now is they will not allow it to die down to abandonment. So what they'll do is at a certain point, they come in now with water flooding. The water flooding comes in now and increase the rate. But remember that it will increase it up to a point and it also starts dying down also. And when it starts dying down, there is nothing you can do. No matter the amount of water you inject in that reservoir, the oil rate will not increase. You instead, what will instead happen is you instead have more water that is produced. So it's like you're wasting energy because you inject water and you produce water. So what's the cause? What's the reason for the operation? Because our interest here is to have oil that is produced at the end of the day. That's our interest here. So what will happen is when the water flooding performance increases the oil rate, there will come a time where it starts decreasing. And at that point in time, it means that the water flooding activity is no longer of interest or is no longer viable for us. So it means that we have to get now to another source of energy. That's where they now bring in the tertiary method, which we talk of the enhanced oil recovery method to see how we can improve the performance beyond the water flooding. And these other methods are what we have: the thermal method, the gas injection, the chemical methods. We have the microbial activity, where they might send in some microorganisms into the reservoir to eat up the hydrocarbons and reduce it from very large chain hydrocarbon to smaller chain hydrocarbon. Our essence here is not to talk about enhanced oil recovery. Anyway, so let's move ahead. So that is what is going to happen with our overall recovery. So if you are to follow only the primary method, you realize that the overall recovery will end somewhere around here. But somewhere along the line, they introduce the water flooding method. So it actually increases the overall recovery, same with the tertiary method. So you look at the various types of mechanism, then you see how each of them contribute to the general recovery of that particular system, of that particular operation, not system, of that particular operation. So we are talking about rock and fluid expansion. The recovery is very, very low, 3 to 7% of it. So naturally, when it comes to water flooding, there are three aspects that we talked about when it comes to water flooding in order to analyze the recovery factor due to that water flooding activity. Because the equation is always, what is the recovery factor at the end of the day? At the end of this water flooding activity, how many percent of the hydrocarbon am I going to have? Am I going to have 10%, 15%, 30%? How many percent of the hydrocarbon will I have at the end of the day? All of that is based on analyzing three types of efficiency, which we talk of displacement efficiency. What is the horizontal distance that the water must have traveled during that particular process? That's what we talk of displacement efficiency. When we talk of vertical swept efficiency, we are talking about the vertical height of that water flooding activity. What's that vertical height? Then when they talk of the aerial swept efficiency, they are talking about at the end of the day, what is the area of the reservoir that the water must have occupied at the end of that activity. So all of this put together is going to give us an idea of recovery efficiency. But that's not our main point of today. So there are various ways in which they have to design the water flooding activity. They don't just go ahead and just say, okay, just drill a well there, then the well will just travel and then move somewhere, and then hydrocarbon will be produced in another well. No, they have to, there's some kind of a plan that has to be put in place. So there are different ways, there are different patterns in which they can easily follow. We have the peripheral pattern, we have the injection wells. These are the injection wells at the periphery. Then we have a series of producing wells at the center of that injection wells. Then we have a regular pattern where we have maybe producing wells that are arranged in this manner. Then we have our injection wells at points. So it easily forms something like a rectangle. Then we have an injection well, water injection well at the center of that rectangle. Then we may also have an irregular pattern. We must have an irregular pattern. There are different types of pattern that you're going to look at. I'm going to provide a PowerPoint. There are different types of pattern. Our main interest here now is what we call fractional flow analysis. That's our main interest of today. What is fractional flow during water flooding? What fractional flow now is the flow rate of water compared to the entire flow rate. Remember that as you are injecting, if this is our injection well and you are producing at this point, at one point in time, at the beginning of the injection, the water is particularly at this particular level. As more and more water is injected, the water is gradually moving. The water is gradually moving towards the producing well. So this particular line is what we call our waterfront. That's our waterfront line. So at that waterfront line, oil is moving and water is also moving. That's one disadvantage of water flooding. You cannot stop the water from going, because if you stop the water from going, then what is going to push the oil? So at one point in time, we expect that the water cut, the amount of water that will be produced in this well will also increase, because the water that is injected, part of it now will be produced at the producer. So that's one disadvantage with water flooding. So at the waterfront, oil is moving and water is moving. What is fractional flow? Fractional flow now is the flow rate of water compared to the sum, to the total flow rate of the fluid, that is inside the reservoir. And then remember, we can also have a horizontal reservoir. We may have an inclined reservoir. So this is just a general case. We might now move to a specific case where the reservoir is horizontal. So now, if we go back to our basic law, which is generally our Darcy's law that is used to characterize fluid flow in porous medium, this equation may be complex. It may look complex, not that it's complex. It may look complex, but the only difference between this equation and the Darcy's equation that we have already seen, because I explained that particular equation last week, or even if I didn't explain it under nodal analysis day 1, you can look at it in nodal analysis day 1. So this is generally our Darcy's law. This is generally our Darcy's law. And the Darcy's law is simply telling us that the rate at which fluid is going to flow is directly proportional to the pressure drop per unit length. Is directly proportional to the pressure drop per unit length. So this is our Darcy's law that is used to calculate permeability. I'm not sure you can complete year 1 in any engineering field without talking about Darcy's law. So I believe that all of us here must have heard about Darcy's law. Let me take this off. So if we are now talking about an inclined bed, then this particular gravity component now comes in. Remember that if a bed is inclined, there is also an additional force that is pushing the hydrocarbon downward. That is pushing the hydrocarbon downward. And that gravitational force is probably a force that is parallel to the plane of movement. It's parallel to the plane of movement. I don't want to go into complicated mathematics. But what you have to just understand is this component is coming in as a result of that inclined plane. So if the plane is horizontal, then the angle is 0. Sin 0 is 0. So all of these components does what? Disappears. So all of this now is still the same thing. We are talking about flow rate of oil. Then we are talking about the flow rate of water. Remember that this flow rate of oil can also be replaced at one case. The flow rate of oil can be what? Can be equal to the not the flow rate, sorry, with the permeability of oil can be equal to the relative permeability. Remember, we talked about relative permeability at one point in time last week. That was our first session last week. We talked about relative permeability. So the permeability of oil will be equal to the absolute permeability multiplied by relative permeability. We talk about relative permeability of oil is equal to permeability of oil divided by absolute permeability. If I make this guy the subject, this term will simply cross. So you might see an equation where instead to see the permeability of oil, you will see absolute permeability times the relative permeability of oil. You might see that in a particular case. So I'll take this off. So if I take these two formulas now and I replace it in this particular equation of fractional flow, I put the flow rate of water here, the flow rate of water here, and the flow rate of oil here, I'll end up having this particular equation. Our essence here is not to go into the deep mathematics of putting it and try to see how this will come out. No, that's not our essence here. All right, so if you put all of that, we are going to have this particular term here. And you realize that in putting all of that together, an additional term now comes in that is due to capillary pressure. The change in capillary pressure as with distance, they change with capillary pressure with distance. Generally, for simplicity case, we are going to assume that this particular term is 0. So if you are working in with field units, remember there's a big difference between field unit and SI unit. There's a big difference between those two things. So if you are working with field units, then some conversions will come in, then you now have this particular term that will surface. So if this particular capillary pressure is 0 for simplicity case, then we are talking about horizontal reservoir, then our angle is 0, then sine 0 is 0. All of these terms disappears. So it means that all of this becomes 0, and 0 times anything becomes 0. So all of these particular terms automatically disappears. So all of these terms automatically disappears. All right. All of these terms disappears, and we end up with a fractional flow equation in a simplified form as this. All right. So our essence now is to use this fractional flow equation and see how we can analyze to know what is going to be the average water saturation at water breakthrough. Water breakthrough simply means that the water that is injected, part of it now is produced at the producer. Once we start seeing signs of injected water at the producer, that is what we call our water breakthrough. So we want to now use this fractional flow equation to see how we can calculate the average water saturation at breakthrough. So we are going to go to our Excel. Remember, this is our equation that we are going to use. So we go to our Excel sheet. What has been given is the water saturation. The relative permeability of water has been given. The relative permeability of oil has been given. We also need the viscosity, because if we look at the formula, we need the viscosity of water and the viscosity of oil. So we are going to just take the viscosity. Let me take insert. Let me insert a figure for viscosity. All right, that's our viscosity there. Take. Insert, all right, close. Viscosity of oil, let's put our 0 there, is equal to, let's say, 0.9. Remember, I said water flowing activity goes for very light oil. When it cannot go for heavy oil. Because if the oil is heavy, the most appropriate technique is to apply maybe steam injection, so that the steam will go and break the long chain hydrocarbons into what smaller chain hydrocarbon and make it lighter. So we are going to use a constant oil viscosity of 0.9, and then we use a constant water viscosity of, let's say, 1. The constant water viscosity of 1. All right. So from there now, we want to calculate our fractional flow. Our fractional flow FW. So I will start here. What's the formula? 1 divided by. So remember, in Excel, we have to always start with equal to when we want to put a formula. 1 divided by, so we have our slash. We will put everything down in brackets. We'll put everything down in bracket. 1 plus 1 plus. We have relative permeability of oil. Relative permeability of oil. 1 times viscosity of water. That's viscosity of water times 1 divided by viscosity of water times the viscosity of oil. I'll close the bracket. I hope there will be no error there. Okay. Actually, no calculation. All of this shows that there's an error. Remember, we have divided it with B3, and our B3 here is 0. Remember, if the denominator of a fraction is 0, that fraction becomes undefined. So once the denominator is 0, it becomes undefined. But it doesn't mean that the formula will not work. So we'll just take it down. All right, so I think let's do some adjustment. There's an error there. Let's do it gradually. I will come to the formula where I have D24 and D25. All of these things are constant. I will highlight them, and I put the dollar sign there. Hold on, not highlight. I'll put a dollar sign before and after. I'll put a dollar sign there. I'll put that dollar sign there to show that it is constant. Then here also I put a dollar sign to show that that particular thing is constant throughout the formula. It's constant throughout the formula. All right. Let's hope it works, because it's Excel like that. Let me see. The dollar sign times. Where is this E3 coming from? Oh yeah, I could probably point something. So what we have there is D24, D20. No, not D24, is D25. And then we have our dollar sign before and after to show that it's constant. D25. What are they saying? All right, to make it simplify so that we don't waste time here. So down here, what we are going to do is we have our 1 plus relative permeability. So we have relative permeability of oil times. Since this value is constant, the relative permeability of water is 1. We are going to put 1 divided by relative permeability of water times. This value is 0.9. So we have 0.9. Then we close it. Yes. All right. I hope it calculates this time around. All right. So we have our fractional flow. There. We'll just put our 0 here. We'll just put our 0 there. So that's our fractional flow. Now we want to draw a graph of fractional flow against water saturation. We want to draw a graph of fractional flow against water saturation. I will come here, I will choose this. I select my data. I'll be fast here because we already know how to do all of this. I will just write there fractional flow curve. Fractional flow curve. For my x values, x axis is water saturation. The y axis is fractional flow. All right, so we have our fractional flow curve. We'll come here and we can add axis title. We'll just write the axis title. All right, that is already there. So we'll change this. I can increase the size before I change. I can increase the size to, let's say, 18. I bold it. Then what we have there is our SW. I will highlight this. I increase the size. Too big. All right. I bold it. What we have there is FW. All right, so that's our fractional flow curve. I can hold it here and drag like that to extend it. All right, so that's our fractional flow curve to show how the flow rate of water is changing as more and more water is injected into the system. So what I will do is I will come to insert. I want to draw a straight line. Okay, on that format, I will take my straight line there. I will start from this first point. Remember, the first water saturation is always the irreducible water saturation. The water saturation are below which no water can, or no matter how you pump, that water cannot leave that system because it is held on by capillary action. So I will take it from this point, and then I make sure that it touches the graph at that point. I will take this axis and change the scale. Let me change the scale of this axis because it cannot be above 1. Fractional flow always ends at 1. So I will take this right up to this point and make sure that it touches. My interest is to know where it touches. We can always have different views. So I will increase the size. I will increase the size of that. I'll go to weight. I will increase the size. All right. I can change the color there. So my essence now is to pick the point at which this line touches the fractional flow curve. So if I pick that, if I try to look at something, like format, if I look at it, I could pick somewhere. Anyway, yes, this point is not bad. It's falling on it. So I will pick it around that point, like that. Change the color. I can also pick it there to get the fractional flow. At that point, I will change the color. So if I pick this point exactly, if I put my mouse there, since it's a point that is plotted, the water saturation there, the water saturation at that point is 39.1. 39.1. That's 39.1. So at breakthrough, the water saturation at the frontal water saturation at breakthrough. So we'll just, let me close this. So we'll just put breakthrough analysis. Breakthrough analysis. So water saturation, frontal water saturation at breakthrough. At breakthrough is equal to, so it's equal to, this is the value 39.1. That's the value there. Just put equal to, and then I have that. And then we need now to also get the average, because if I go back to my PowerPoint, you have to realize that as time is going, you are doing more and more injection. The water saturation at this level will not be the same as the water saturation at this level, because as the water is going, it is pushing oil. The next water that is coming, there is not much oil that is left for it to compete with. So the water saturation will gradually be increasing in this direction. Here I'll have the lowest water saturation. Here I'll have the highest water saturation. They have the water saturation at the front. True. But what we want to also get now is the average water saturation behind the front. What is the average water saturation behind this front? All of this area that have been swept by water, what is the average water saturation at that particular level? The average water saturation is obtained. So I'll click on this, I'll see format. So the average water saturation is obtained at this level. The point where that straight line touches that horizontal value from 1, that horizontal line from 1 is where you get your average water saturation behind the front. That average water saturation. So we get that value there to approximate it. So we'll just say average SW at breakthrough. So we can estimate this value to be, if this is 40, this is 50, we could estimate it around 48. So let's just estimate it about 48, around 48. That is the average water saturation. Remember, it is in percentage. It's in percentage. So don't get confused as asking why is it like this. It's in percentage. If you look at the water saturation here, it's in percentage. So our water saturation, the frontal water saturation at breakthrough is 39.1, and the average water saturation behind the waterfront is 48%. That's the average water saturation. So that's our essence for the class of today, is to do some water fluid analysis to evaluate and calculate the water saturation, the frontal water saturation, and the water saturation behind the front. So this is just a key aspect of water flooding analysis. There are so many calculations that we can do. It's just that the calculations are so complex. I didn't want to I mean, you can go, I mean, if you go into the reservoir engineering handbook, you get a whole lot of calculations that you can do from there. We can calculate a breakthrough time, the time that will take the water to move, that waterfront to move to the producing well. It's just that the formula was so complex, so I didn't want to get into that. I didn't want to get into that because you have to calculate what we call df on ds slope and plot, and then you start picking points and all of that. So it's so complex. So we cannot get into that. At this level, we just do the basic, then you can go into that. You can go into that at your own leisure time.